plane with any known device. It's created by the size, the external shape. I'm not sure how much that's really used out there in the industry, you know. And they have so very little about it. You know, it's just, this is possible. Someone may specify it this way. You're going to be using the outside shape to determine what that medium plane looks like. So I would just stick with standard flatness control, you know, myself. Then, of course, there may be just a certain area we want to be flat where it's going to contact another part in that area. So we will specify it with basic dimensions and call out the flatness. Then there may be necessary to control the flatness of a given surface area as a means of controlling an abrupt surface variation within a small area of the feature. So we can use it alone or in combination with a total tolerance. Then circularity. It's a cross section taken perpendicular to the axis, and the circularity geometric tolerance zone must be less than the size tolerance. Okay, so it has a restriction on it. Okay, must be. In the other situation, it was, you know, for straightness of a shaft, you know, it can fluctuate. You know, you can use it either way, but when we're talking about circularity, it has to be less. Because we're checking the circularity, which is two parallel circles, concentric circles, it creates like a tiny, infinitely thin zone. It's in just that one area. And wherever the arrow is pointing is what we always used to tell our quality control or production personnel. Is where that arrow is pointing, that's where you measure. Measure one place. Might need you to check in two places. We might specify that. But it's just check in one place. You don't check over the whole. For circularity, it's in one circular element. Okay? It's a pretty easy concept for geometric. Then there's the free state variation. Again, I kind of touched on that earlier. So distortion can happen to thin wall parts where the weight and flexibility of the part are affected by internal stresses applied during fabrication. So if they're real thin parts, it could even be metal, not necessarily rubber, but if it's extremely thin, tiny part, you know, it might heat up during manufacture, and then when it cools, it could change shape. And then the same thing with rubber or any kind of the plastic kind of parts. They all distort, change shape. They're dependent upon the surfaces or other parts that hold them to determine what they're really ultimately shaped like, or what they'll be shaped like upon assembly. As they're squeezed or pushed or stretched. Okay? So we refer to them as non-rigid. So we have to do a thing that's kind of interesting. We actually measure. We'll create a drawing, for instance, for an O-ring, and because of this flexibility and non-rigid state, we'll actually provide a kind of a limit tolerance, but it's an average that might be measured in 4 or 5 places, at least 4 places is what that means to do. Okay, 4 measurements taken and averaged must be between this range. So a lot of testing, manufacturing, testing, assembly, measuring, figuring it out. So it's difficult for something, for the drafter, designer to just dream up, looking at his screen. You're going to have to depend on, it might be your job to create the situation and measure it up, and see how it performs over a range of parts, or an engineer or some technician, tool maker, whoever might be doing it. Okay? Then controlling the circularity. And this is what we call a restrained condition. Okay, so when it's actually kind of simulated assembly. So what you see on page 194, specifying restraint for a part with a datum feature controlled by circularity geometric tolerance. So this particular part here would be like a fixture. The best that I can see is what we're looking at here. Okay, the circularity is specified, and it's actually part of the data. And but it's given an average, so this could actually be the flexible part, some kind of rubber boot, perhaps. Okay. But I kind of looked at it at first and was thinking, well, maybe this is a mating part, almost like a gauge that we're building. So the maximum forces necessary to restrain each feature are specified when the surfaces are subject to free state variation. The forces are established as needed to simulate the expected assembly conditions. So basically we're specifying it when as it's restrained. And so whatever this is fitting upon would restrain it. This tolerance applies when the data feature is mounted against a flat surface using 4 bolts torqued while restraining data feature B 9 to 15 nanometers. That's fairly light. Or I'm sorry, Newton meters, not nano. Nano is a small unit. So that's Newton meters. That's still pretty light torquing. So as this is torqued down, it puts stresses on this part, and so the tolerance is going to apply. In this case, showing a tolerance that we haven't covered yet, run out of a single line. Okay. Cylindricity basically takes the circularity and runs it as across the whole surface. So circularity is cross-sectional between 2 concentric circles, and cylindricity covers both circular and longitudinal elements at the same time. So it's 2 concentric cylinders, like a tube. we don't really get into all the ins and outs of it very much. It's kind of the same thing as circularity. It must be less than size tolerance. It's always considered regardless of feature size. So we didn't run a chart and run over that and beat that dead horse again in here. You know what that means now, and you can look at the example of circularity. You know, it's a concept you should have by now. And again, is not referenced to a datum, but it may be used to as part of a datum device or datum setup, but it's not. It doesn't reference a datum, but a datum references it. Datum can be created from it. Okay, it's like this pen. This is a pen, and we're going to use this as part of our datum. And that pen may have certain cylindricity controls on it. So as it's stating here, the very last thing, what I was saying, form geometric tolerances can be applied to datum features specified on the drawing by attaching the datum feature symbol directly to the form control. This is pretty unusual. We usually don't have room to do it like that. Usually we'll attach it to the bottom of our form control frame. Okay. That about sums it up. The form tolerances, 4 characteristics. Just to recap: straightness, flatness, circularity, cylindricity. Applied at RFS or at MMC, we have straightness tolerance of a shaft. We can apply it to the axis and use MMC. We can control a unit of measurement and apply straightness to it. And then over the whole length, or just a portion of a part can have straightness control. We can apply it to a rectangular or prismatic part, flat surface that is. We can apply it as flatness to parallel planes over the whole surface, and it's controlled by the MMC unless we use the independency symbol. To a lesser degree, control the median plane. We can control a specific area for flatness using basic dimensions. We can say that per unit of measurement it must be flat to a particular specification. So over the whole surface or per unit. Then circularity, 2 concentric circles, regardless of feature size. No datum reference required. Then cylindricity. Then we also use circularity for non-rigid parts, thin non-rigid parts.